Okay, um, this one, we're going to give another shot to this. Hopefully it's going to be posted on the website. Otherwise, you guys will be watching it in class again like we had to do before. So lesson P2 is on exponents and radicals. And just a heads up on one, there is a lot of information in this section. Again, it is stuff that you guys have covered in the past. But be prepared to pause and take notes and do all that stuff as we're going through these slides. So we all know that to represent a repeated multiplication, an exponent can be used. So for example, 6 times 6 times 6 times 6 is represented by 6 to the 4th power. The base is the large number, in this case the 6. The exponent or the power is the 4, and that just simply tells you how many of the bases you're going to be multiplying together. All right, so real basic review. That's right back there to about 7th grade. Now on this slide, there are a number of things that you will be expected to be able to perform involving some properties of exponents. So first, if you would turn to page 14 in your textbook, there's no way that I could figure out how to type all of these again in under 40 slides. So I'm going to leave it up to you to take a look at these properties and transfer any of them that you don't remember or think you might need to recall into your notebook. The first property, a to the m times a to the n. Okay, notice that the a or the base is the same. So then when we multiply same bases, you end up adding the exponents together. So for example, 3 to the 3rd times 3 to the 4th is going to be 3 to the 7th. The next one, if multiplying same bases together has you adding the exponents, it makes sense then that dividing same bases is going to have you subtracting the exponents. All right, so that's what you see there in property number 2. Number 3, this is one that comes up a lot, the negative exponent. Remember that getting rid of the negative part of the exponent is achieved by doing a reciprocal type of action. So where you have a to the negative n, if you switch that to the underside of a fraction bar, now the power of a is going to be a positive n. Okay, so a to the negative n turns into 1 over a to the n. Number 4, remember anything to the 0 power is equal to 1. If you have, like number 5, where you have a times b raised to the power, anything inside that parenthesis is going to get that power that it's outside the parenthesis. So that's why it's equal to a to the m times b to the m. And then 6 is kind of the reverse of that. If you have, or no, it's not either, a power raised to a power, now that's when you multiply those powers together. So for example, if you had x squared raised to the 3rd power, you're going to have x to the 6th, 2 times 3. Number 7, anything in the parenthesis again that has that power gets the m. All right, so you don't have to leave it in the fraction form like that. You could pull it apart. So if a over b is in that parenthesis and the exponent is attached to the parenthesis, that exponent goes to everything inside, the a and the b. The last one there, absolute value of a squared, is the same as the absolute value of a squared. Okay, so take a look at that last property, number 8. Now I put a few problems on the slide here, and the main ones that I want you to be taking a close look at, and you'll notice these are found in the checkpoint section that's halfway down page 15. All right, so that A, B, C, D that's in the middle of page 15 are the problems that I transferred to this slide. Take special note of problems 1 and 2. Okay, they're not very much different. What's the only difference about them? Number 1 does not have a parenthesis surrounding the negative 3. Number 2 does. Okay, when you look at number 1, technically, the only thing attached to that power of 4 is the 3. The negative is like a negative 1 multiplied out front, and it is not affected by the power of 4. Okay, so number 1 is telling you that you want the negative of 3 to the 4th. Okay, So number 2 is different than that. Now it is the entire digit -3 taken 4 times. Okay, so number 1 is the negative of 3 times 3 times 3 times 3. Number 2 would actually read -3 times -3 times -3 times -3. Okay, so I'm going to give you a couple of seconds here to try to work out these 4 problems and see what you get. These all use those properties that we were just talking about from that box. And then you can flip to the next slide to check yourself out. All right, so the answers now are in red. How did you guys do? Okay, hopefully not so bad. The nice thing with this textbook, and we're going to talk about this a little bit, do you see in the gold kind of print along with the checkpoint problems in the textbook, it says audio video solution in English and Spanish at larsonprecalculus.com. This is really a nice feature that our textbook has for us. If you go to larsonprecalculus.com, it will take you to a site, and I think you had to pick the cover of our textbook. You'll see 2 book choices there. You pick the one that looks like ours. And then you can bring up example number 1, and it will give you verbal and written out solutions to these checkpoint problems. So without the answers and solutions already done for you, it's really nice practice problems for you guys to be working through. And then you can look through and listen to that video lecture, and it's like having another lecture on top of other problems that you've had in class. So please do check out those larsonprecalculus.com checkpoint ones. They really are going to help you guys a lot, I think. All right, moving on. Give these a try. Okay, so give yourself a couple of seconds to copy them down. Watch out for number 1. There is no parenthesis around the -x, so try to remember how to deal with that. And then in number 2, there is a parenthesis again, so let's see how you do. So when you think you're done, and we click the PowerPoint again, hopefully my answers show up for you guys. Did you end up with negative of 1 over x squared for the first and x to the 4th over 4 for the second? Okay. Again, these 2 I pulled again from a checkpoint section. So if you do not understand the process in the solution, go on and listen to it. Watch them work that out for you. So the next slide says there are several more checkpoint sections on page 16 in the text. Work through a bunch of them. Okay, play around, especially just play around with the checkpoint audio that's provided for us online, just so that you know how to work that option for today and for future lessons. Okay, so there's midway down the page under example number 3, there's 4 more problems, playing around with exponents, using them with negatives, reducing, canceling. All of this stuff, again, is stuff that you have had in the past, but the practice is good. Okay, down at the very bottom of the page, there's another section like that. Okay, so I would like you guys to work through some of those checkpoint sections. All right, the next thing. You guys have used scientific notation now for a lot of years. All right, scientific notation, the whole purpose behind that is to have a way to kind of abbreviate really big or really small numbers. Okay, so for example, if we had 32,400,000 like I have typed for problem A, scientific notation would rewrite that as 3.24 times 10 to the 7th. All right, remember when you're putting things in scientific notation, there's a set format. You can't mess with this at all. The decimal point always goes behind the first digit. Your values will run between 1 and 9 for the digit part. Okay, it has to be between the first 2 numbers. So 1 number in front, anything else, and everything else behind. To get the power of 10, you just count. How far did the decimal point travel to land between the 3 and the 2? So if you come in from the right, it goes 1, 2, 3, 4, 5, 6, 7 places to get between the 3 and the 2. Okay, this works for the little numbers as well. If I have 0.00000708, I want that decimal point between the 7 and the 0. Okay, so 7.08 is the digit part. Then again, I need to find my power of 10. Well, if you count it in from where it is, it takes 6 places to do that. But remember, when we're marking these values that are less than 1 to begin with, or our decimal scientific notations, the power is going to be negative. So it's 7.08 times 10 to the negative 6. Okay, hopefully you guys remember all that stuff. So again, if you wish, there are some checkpoint problems that practice that a little bit more in your textbook midway down page 17. Now, right around example number 7, okay, using scientific notation for a little bit bigger of a problem. There's one worked out in your textbook there for you for example number 7, and I pulled the checkpoint one from the very bottom of the page. Okay, so everybody can see 24 billion times whatever little decimal that is, and then times 300,000. Okay, if you were to do this, that's a lot of zeros and a lot of place values to keep track of. Okay, if we use the numbers as they are. But let's try rewriting it in scientific notation first. So see that that first number turns into 2.4 times 10 to the 10th. The middle number turns into 1.2 times 10 to the negative 7. And then the last one turns into 3.0 times 10 to the 5th. Okay, now we talked in class about that whole multiplication property that lets us take stuff out of order. So we're going to use the associative property and rearrange all this stuff. So I grouped all the regular numbers together, and then I put all the 10 to the powers of whatever's at the end. Okay, so all the three first numbers, 2.4, 1.2, 3.0, multiplied together, that gives us 6.6 or 8.64. Okay, 10 to the 10th times 10 to the negative 7 times 10 to the 5th. Remember your powers properties. If you're multiplying those same bases together, all you have to do is add those exponents up. Okay, a 10, a negative 7, and a 5 give us an 8. So 8.64 times 10 to the 8th power is what we're going to get in scientific notation. And then that's really simple to switch back out into standard form, and we can see 864 million. Okay, that's not so bad. The next page. Okay, they're really throwing a lot of review stuff at us here in this section. We've got radicals in their property. Now remember, radical is a special name for a square root symbol. So radical signs are square root signs. When you're looking at roots of things, please read through the definition of the nth root box that's at the top of page 18. Okay. Some numbers are going to have more than one root. Okay, all of your positive numbers actually have a positive root and a negative root. Oftentimes we're only dealing with that positive root. Our textbook refers to that as the principal root. So if you're ever asked to find the principal root of a number, you're only being asked for the positive. Otherwise, technically, the square root of 25, or the roots of 25, would be 5 and negative 5. But the principal root would just be the 5. All right, turning back to that page 18 in your book. There's a bunch of evaluating expressions down at the bottom with example number 8. Look through the ones that the text has done for us. They have some couple of square root problems. They have a couple of cubed root problems. Okay, that's indicated by the 3 on the outside of the radical. There's a 5th root. There's a 4th root. See how those are manipulated and figured. Okay, and again, there's some checkpoint ones at the bottom of the page that you can take a look at as well. Perfect square and perfect cube numbers are going to have integer answers for square and cubed roots. Otherwise, the other ones have decimal whatevers, and they fall in between. Those are the non-perfect ones. We talked a little bit about this with rational and irrational. The perfect squares have integers, so those can be turned into fractions, and they were the rational ones, and so on and so on. So perfect ones are the nice ones, non-perfect are the ones that end up yucky. Why don't you guys take a look at page 19 in our text right now? There's some more properties of radicals in that one box there, and again, there's absolutely no way I'm going to retype all these. So you guys are more than able to look at page 19 in the middle of, or in the middle of page 19 for those properties. Some of these are a little bit confusing. Work through the number ones as well as the ones with the letters to the left. So look at the examples as much as you're looking at the property itself. Makes a lot more sense. Then try giving these a chance. Okay, we'll give you guys a couple of minutes to work through them before I switch over to answers. Okay, I'm back. Let's see how you did. So the top one there, you can reduce or divide radicals with other radicals if the numbers go into each other evenly. So one of those properties on that one page showed us if you had the square root of 125 divided by the square root of 5, 5 goes into 125. Okay, it goes in 25 times. So the two of them divide and give you the square root of 25, which is 5. The next one, the cubed root of 125 squared. Okay, that can be written as the square of the cube root of 125. Again, that refers back to one of the properties that's on that box page. Let's see which one I want you to look at. The first one. Okay, so just like up on that box one, the numbers can be manipulated that way as well. Now the cubed root, remember, means something times something needs to equal 125, and 5 times 5 times 5 does. So the cubed root of 125 gives us the 5, then we tack on the squared, and then 5 squared is 25. Okay. Number 3. This one has two cubed roots being multiplied together. You have the cubed root of x squared times the cubed root of x. Since they're both cubed roots, go ahead and multiply them together. What's x squared times x? That's x to the third. So now we have the cubed root of x cubed, and I'm not sure why I didn't type in the x there, but the answer to that, all in all, should be just plain out x. Okay. Now with square roots, they don't put the little 2 on the outside. It's just assumed that when it's a plain radical sign that there is one. But for this one where we're taking the square root of a square root, it's kind of helpful to put it there. So I wrote in the 2's along with the root symbol, and it's a little bit easier to see how the square root of the square root of x then turns into the fourth root of x overall. Okay, and again, that follows one of the properties that can be located in that box. So there's a lot of different ways that we can play around with our radicals, and it's kind of a blitz and a guess as to kind of stuff that you're going to see. You can see there's quite a variety that's given to you here. Again, those 4 problems that I had on that slide were the checkpoint problems at the bottom, page 119. So if you want the explanation again from their site, you can sure go to that larsonprecalculus.com and listen to it again. All right, we are still not done. So turn now to page 20. We're going to be doing some work with simplifying and radicals. Couple of things to remember when working with your radicals, you have to simplify until all of the following have been completed. First, perfect square factors have been removed from the radical. all fractions have no radicals in the denominator. I don't know if you guys remember from the past where you were rationalizing denominators. If that term sounds familiar, that's what that means. Get all of your square root signs out of the denominators of your problems. And then number 3, the index is reduced. Okay, now what they mean by index is that little number that's on the outside of the root symbol. Okay, that is defined in the book, but don't know how many of you guys actually had read through that and caught that. Okay, so when they refer to the index being reduced, they want you to do the cube of the number or do the square rooting of the number or so on. Now, pages 20 to 21. If you look in your book, there again are a ton of checkpoint problems with a variety of things that you're going to be seeing, including rationalizing denominators at the top of page 21. Definitely want to take a look at those, go through the checkpoints again. The main one I want to direct you guys back to is number 13 at the bottom of page 21. I know you guys saw this in Algebra 2 because I worked with a number of you that quarter that I took over, and it dealt with conjugates. And I think that word maybe, hopefully rings a bell. But when you have something like square root of 6 minus square root of 2 in the denominator of a fraction, you can't leave them there. And it's not as simple as when you have a single square root where you can just simply multiply it by itself to make it disappear. You got 2 terms down there. But what we can do is take square root of 6 minus square root of 2 and multiply it by the square root of 6 plus the square root of 2. That's called the conjugate. When you FOIL those binomials together, the f, the root 6 times root 6 is good to go. That's going to give you a 6. And the root 2 times the negative root 2 are good to go. And if you notice the insides, you're going to get a negative root 12 and a positive root 12. They're just going to flat out cancel out. So that's why this conjugate thing works, to eliminate those square roots on a 2-term denominator. Okay, so take a look closely at the slide here and look at how that works itself out on the bottom. It's just a FOIL technique. You guys remember how to do FOIL. We do actually talk about that more in the next section. But maybe that rings a bell for you guys. There was a reducing thing at the very end because the bottom ends up turning into a 6 minus 2 or a 4. So on top there was an 8, the bottom there was a 4. Always look for that reducing with your regular numbers too. Okay, if that makes absolutely no sense, please come back to class with some questions on that for tomorrow. All right, I have never seen examples where they've rationalized the numerator before. But example number 14 on the following page, it's using the same exact concept to get square roots out of the top of a fraction. I'm just really not quite sure when that's going to pop up that you have to. Okay, it's always kind of the given thing that your answer is not done until the denominator is rationalized. I've honestly never seen rationalizing numerators before. I don't know when you're going to use that. Okay, take a peek at it. Okay, still on page 22. Couple more things for you guys to take a look at here. There's another way to rewrite radical problems. Okay, so if you've got the square root of x, it's the same as saying x to the 1/2 power. If you have the cubed root of x, it's the same as saying x to the 1/3 power. 4 to the 3/4 power, sorry about how that looks typed, but it's best I could make it end up looking. Remember when we take a power to a power, it's like multiplying them together. So if we had a 4 to the 3rd raised to the 1/4, that would be 3 times 1/4, and that's how you would get that 3/4. Now we can swing that 1/4 around and make it the 4th root of 4 to the 3rd. So it's just a lot of playing around with how you can rewrite and reinterpret these radical things. Okay, so if you had the cubed root of 6 squared, that could be written as 6 to the 2nd power raised to the 1/5 power, and those two multiplied together are what result in that 2/5 that you see on the screen. Try working through examples 15 through 17. See what you think. Again, there's some checkpoints ones if you want to see if you understand. Work a couple of them, listen to it through, and see how you did. All right, folks, that was huge. So this is what I was talking about when they cram 1,000,001 review concepts into one section. So you've played with this stuff in the past. Some of it's just remembering the properties that allow us to rearrange and play with things now. Um, just come with questions when you run across a problem that you don't understand, and we'll try to pound those out together. Okay? So what I would like you to do for your practice problems this time is go to pages 24 to 25. Now the problems are numbered 1 to 84. Start at number 9 and do every third one. So you're doing just the multiples of 3. So 9, 12, 15, 18, on and on and on and on and on. Okay, so that'll end up roughly being 25-ish or so problems. That's not too much to bite off. So if you want to get a start on that tonight, great. Otherwise, if you've already watched the video and taken your notes, you've got class time tomorrow to do that. All right, we'll see you guys in class.